Okay, good morning. I'm going to share with you some of the amazing manifestations that occur in nature, and we're then going to focus on some recent work that we've done to address a particular case of that. It occurred to me this morning, it was 20 years ago this year when Alon Bergantz and I first submitted our paper invoking explicit concepts of multiphase flow to explain aspects of pyroclastic flow mechanics, and I feel like we're still just getting started. A lot of the work I'm going to show you was done by Alex Carrera, who's a postdoc with me, who's just returned to France. This is the view when I step outside my office in Seattle, Washington. That's the large volcano, Mount Rainier. And when we look at images like that, it reminds us, of course, immediately of the potential hazards these volcanoes pose to communities nearby. But there's a lot more interesting science that can come out of looking at volcanic systems. This is just the surface expression of a process that has started in the deepest part of the Earth and is transporting energy, mass, volatiles from the deep Earth to deep space. And this kind of process has been important in forming the atmosphere and conditioning the crust and hence the environment for life. And so what I want to do today is talk about some of the ways in which this fabulously complex system is really manifests most clearly as a multiphase flow system. Now, in honor of all my French colleagues who have taught me so much, I wanted to share with you my favorite particle. This is my 2CV in Seattle, and it is a kind of Lagrangian particle, but it's very rarely inertial. With only 2 cylinders, we rarely get a Stokes number above 1. If there's a headwind, I might have a very low Stokes number. I really like, if you have questions about the car, those are the ones I want to hear about. Okay, so what I want to do is kind of touch on this notion that volcanic magmatic systems have a dual nature in their mechanics. Let's start with this example. This is the Pinatubo eruption from 1991. It's quite obviously very explosive, very powerful. These kinds of volcanic behaviors can have volumes of up to 10 to the 3 cubic kilometers in terms of their mass. They often penetrate the tropopause, as Pinatubo did with a 40-kilometer high column. This is important because once it gets up, and the material gets into the stratosphere, the gases and the ash, it can be distributed quite widely around the planet and disrupt everything from air travel to climate effects. These things can happen very quickly. The rise time of unrest to eruption and to the cessation of eruption can just be a matter of days. Okay, so this is one kind of end-member behavior, the high inertia number manifestation of volcanic processes. There's a whole nother side to what's underneath the volcano, maybe as expressed by the world's great batholiths or bodies of granite, of which Half Dome in Yosemite is a nice example. These are very different. They're also very large. They exist anywhere from 10 to 50 kilometers within the Earth's crust, and they can be enormous. And they are basically mixtures of crystals and silicate melt. They can have volumes of up to 5 times 10 to the 5 cubic kilometers. We know, how do we know that? We know that from seismic imaging, because they have a distinct change in the way in which seismic waves propagate through them that can be measured. They can persist for up to 1 million years in this kind of state. They are, and this is the factory for crust building. This is where a lot of the processes that ultimately culminate in a volcanic eruption are created, emerged, and modulated. So if we want to model these kinds of processes and use physics as a way to probe their behavior and why they do the things they do, that's always the question, right? What is the underlying template that produces the same phenomena in nature over and over again? So if we want to somehow make a model, whether it's for hazards or to better understand and learn things about a process, we have to create an inventory of the phases that are involved. The discrete phases are typically ash or crystals, small crystals that grow inside these magma bodies. Their density is on the order of 10 to the 3 kilograms per meter cubed, and they can have a size of 1 to 100 millimeters. And there's bubbles. We're not going to talk about bubbles today. The continuous or carrier phase can be quite different depending on the system you're in. It can be typically air or air with water vapor and hot volcanic gases. Density of around 1 kilogram per meter cube, dynamic viscosity of about 1. On the other hand, if you have silicate melt, the conditions are very different. The density is about 10 to the 3 kilograms per meter cube, so the density ratio between the crystals and the melt is around 1, and the viscosity can vary enormously. And not only does it vary, it's also very dependent on temperature and water and volatile concentration. So this adds, we can really see there's a strong difference between this kind of system and one that's where the carrier phase is mostly air. So if we translate that into some dynamic parameters that we're familiar with, just very roughly, Reynolds number in these kinds of systems can be up to around 10 to the 7, and the Stokes number can be highly variable depending on the turbulent structure and the size range of your particles. You can have everything from ballistics to fine ash, which is moving as a tracer. We get a lot of entrainment and buoyancy reversals in these explosive eruptions that kind of characterize the overall kind of kinematic template. And sedimentation occurs not only from ash raining down, as we saw some work on that, from clouds that are being carried by the ambient winds, to gravity currents that form pyroclastic flows, and you're going to hear a lot about that this afternoon. Conversely, in this kind of environment, we have Reynolds numbers are generally much, much lower than 1. Stokes numbers are very, very low because of the effect of viscosity. And we have a very interesting and poorly understood variety of instabilities that can take place, from double diffusive effects as the melt composition changes, as crystals grow. You can have melts that are lighter, hotter, or colder than their environment. You get sedimentation of crystals coming out through time out of these magma bodies. They can also undergo a type of mechanical compaction. You can get particle Rayleigh-Taylor instabilities that are either positive or negative depending on changes in their environment. So there's a very rich set of portfolio of possible dynamic states that can emerge in these systems. And this is one of the things we want to probe today. Now, I'm not going to talk any more about the inertial range because that's this afternoon. I'm going to focus now on the crystal-rich dense phase state. Let's take a moment to marvel at this outcrop. This is my namesake outcrop. It's in Yosemite National Park. It's actually called the Bergantz outcrop. Not that I've made any progress on understanding it, maybe because I just hang out there a lot. But let's take a look at this. This is what you might call generically a granite. And we see a number of things immediately with the eye. You don't need to be a geologist to notice. There seem to be these white things. These are large crystals that have some sort of alignment. There's things that are cross-cutting. There's both distributed and localized deformation, all kind of captured in the snapshot. So this is the kind of the expression in nature that tells us that even though Stokes numbers are low and Reynolds numbers are low, they are still producing things like this. And the reason we care is because in this crystal-rich environment is where a lot of the compositional changes, the volatile changes, the things that produce ore deposits and so on, and create the character of the crust are taking place. Unfortunately, we can't access it when it's living. At the scale. We can do experiments, but it's very difficult to do them.
So this white line that goes across, that's real, right? That's quartz or something?
Yeah, this is a little teeny later intrusion. There's two of them. There's one up there and one down here.
Oh, they're later. Okay.
Yeah. So this is what we call a crystal-rich mush. And this type of suspension is we actually found initially much harder to understand and deal with theoretically than the dilute case, because it wasn't clear who's controlling the dissipation at any given time. Because you can see that, so if we want to address this in its natural state, it's obvious that the particle sizes and shapes vary. So we have to respect that kind of feature of the natural world in our approach. There's a very strong crystal fabric. We're going to talk about fabric. Fabric simply means the orientation, the net orientation of all these little particles, objects, or crystals, which is something every geologist can measure. And it ends up controlling the permeability. It ends up controlling the strength. Because we know as you develop a fabric, it's a form of shear thinning. And there's localized and distributed deformation. So this is kind of a yellow light about simply invoking a rheology, since the nature of the deformation and strain is changing progressively as flow goes on. So if I go into Doug world, where does that kind of stuff live? And I'm just using a viscous number here, but it doesn't matter, as Doug said. It's really unimportant in the quantitative part. That's not it. The magma mushes live up here in this corner, in this kind of range of solid fractions, and this kind of, I've been very generous, range of viscous numbers. Next time you do this figure, we'll include the magma mush. So if we want to understand the mush, what our approach was, since it isn't easy to do we want to understand the micromechanics, and that's hard to do in a rheometer. You get the bulk behavior, but we wanted to understand the micromechanics that are controlling this. So what we did was we obtained a sample from the Massif Central to say, well, what is the size and shape that we should choose to interrogate? And so what we did was we chose a shape distribution of this, like this, and aspect ratios like this. And we're going to look at two classes of particles, one oblate and one prolate, and ask ourselves, when we mix these two, how much does that control the formation of fabric? That's the focus for today. There's a whole lot of other stuff that can be talked about, but I don't have enough time. So what we did was, over a period of 2 years, Alex did 22, because there's an infinite number of ways you can combine shape and size. But this constrained that. He did 22 DEM-CFD simulations with 14,000 particles. The particle shapes were the template for the particle shapes we used was a superquadratic, which is basically you're kind of taking a football and pushing it into a sphere or smashing it into an M&M or something like that. The fluid is unresolved. In other words, the fluid cell is larger than the particle. I think it's okay when we're in the dense phase case to do that. And that's solved with the finite volume method. The DEM was just your classic soft contact type DEM model. So here's the setup. Here's the physical properties. That's probably not all that important. Here's the numerical experiment setup. It's basically a stress boundary, not a fixed volume boundary. We have a normal pressure. We exert a simple shear on top and bottom. The melt phase can enter or leave. Of course, this did dilate, just as you might expect it would. So we have a fixed plate on top. That's our pressure plate. To that, we glued a layer of particles, so the coordination number and roughness character would be appropriate for that top boundary. So the particles that are being sheared are looking at particles that are like them, rather than something that's half spheres on the top and bottom. So we basically randomly seeded a volume, let those settle, and then compacted it slightly. Then had a slowly increasing, we basically then started the motion and then held it constant. And let me show you an example, and we can, of one of these simulations. This is one where they're all the same shape and size. These are prolate particles. And you can see as basically the progress of shear goes on, they tend to align and the strain moves and the deformation propagates inward from the walls. This is kind of a mixture of prolate, oblate, and spheres. And it's just to help us appreciate the nature and changes and competition, because as one shape which has a preferred orientation wants to get into that sweet spot, it can get bumped out of the way by another one. So we get this, as you'll see, we get this very noisy, steady state that controls the fabric. It wasn't clear to us when we started this that if you sheared it long enough, would it find the perfect fabric? And the answer is no. That competition limits, clamps the strength of the fabric, as we'll see. And that was a kind of a surprise. We don't yet understand the micromechanics behind that.
I was just wondering if you could say quickly anything about the force model between the particles, or what goes into the simulations?
Well, it's just your classic soft DEM. You look at the overlap. Let's talk about that later. Okay. So what do we do with that? How do we measure and quantify this fabric? Well, the beauty of this approach is we have everything. We have the contact, we have the fabric tensors of the contact, we have the fabric tensors of the forces, and now we have the tensors of the particle shape orientation. And we also know the coordination number, and we also know the anisotropies of those tensors. I'm not going to show you much of that. Let's just focus on fabric. So how do we describe fabric? We basically have a single scalar, an order parameter S, that goes from 0 for a random orientation to 1 where if everything is aligned. Okay, and we calculate that using the method of Gao et al. From 2013. And here's an example. You can see at the start of the simulation, they're rather disordered, so the order parameter is low, but as shear continues, it finally reaches some nearly steady state. And visually, you can see that they're very aligned. To a geologist, this is a lineation. So here's some of the results that Alex has obtained. of our order parameter for prolate particles. Now let's do the geological case, the mixture of sizes and shapes that were found in the field and the Massif Central. That's this curve right here. So if you have a natural, so to speak, mixture of sizes and shapes, it's very hard to get a very strong fabric. Fabric improves, but then it hits a limiter. And there's no more benefit. The material cannot improve the strength of its fabric. Now we'll compare that with another end member, which is this one. And what do these numbers mean? Basically, what we have in parentheses, if it's F, it means the size is fixed, and 3 is the aspect ratio. So this is kind of a grain of rice. But they're all the same size. So we can look at the competing effects of size and shape on fabric formation. D means distributed. It's basically, if it's D, it's using one of these for both size and shape. This is size is fixed, shape is fixed at aspect ratio 3. So it's a natural end member. And this run is still going, even though Alex is now in France. But you can see it's the best case scenario, which doesn't really surprise us because of the shear thinning. There's very little shape competition between the particles. And it's probably going to get up here somewhere around 8. Well, now let's ask ourselves if size matters. B2 is a simulation where we had the distribution in sizes, but we kept the same aspect ratio as B6. There isn't much difference. Changing the size spectrum, at least in this particular choice of sizes, had very little influence on the strength of the fabric that was produced. As we reduce the aspect ratio, the strength of the fabric continues to drop. So this is telling us that what's really controlling fabric is the aspect ratio of the particles, which I think is kind of intuitive. This one has the fixed shape, but the distribution of aspect ratios. But the take-home point is that fabric is limited, and we don't quite understand exactly what's controlling this from the micromechanics yet. We just haven't had time to dig into it. We can do the same thing with the oblate particles. The oblate particles are like the flat pancakes of the M&Ms. I'm not going to but I'm not going to drag you through them all. Here's the natural example. Once again, the natural example, the combination of shapes and sizes, is the worst performer in terms of producing a fabric. The reason these numbers are less than 1 is just the way the aspect ratio is defined in an oblate versus a prolate template. If we summarize those results, this might be one way to do it. Here's our order parameter again, going from 0 to 1, random to everything's perfectly aligned, versus aspect ratio for the oblate and the prolate. Let's start with the prolate. So basically, let's look at aspect ratio 2. The black or red dot indicates the start of the simulation. The black or red tip of the arrow indicates the end of the simulation. The fields that are in red this is the size. This is basically the field that's traversed when you have simulations with size distribution, and black if there's just one size distribution. And most of the variation is in aspect ratio. So it's very clear that aspect ratio is controlling the behavior. And this might get down when we look at natural examples, even in geomorphology. Shape matters. It may matter. Another thing that one can measure in the field is something called foliation, which is basically the angle of the preferred angle of the particles relative to the shear direction. And for the prolate particles, that's what this angle alpha is here. They very quickly find that preferred orientation. This can be a little bit noisy. The one that had the natural distribution had the highest angle, about 30 degrees to the shear direction. That's the DD, the distribution in shape and distribution in aspect ratio. Yeah. Okay, there are some caveats that come with this. We observed strong localization in virtually every simulation we've done. And I think there's a certain culture in the modeling community that tries to sweep that under the rug because it's very hard not to get. In other words, the behavior is very non-affine. Even though we have a rheology, inside that rheology, there's probably a lot of non-affine behavior. And that's difficult then to import that rheology as a framework for explanation if we're looking at field examples where that localization is actually controlling the stream or controlling the flow. Because I've seen many examples in the field where you have distributed to localized deformation, switching over what is probably very small melt fractions. So we want to know what triggers that, and what's the possible role for clusters. Jeff touched on this, as has Karen in the past. I'm very interested in that. And also, what is the nature of jamming when you have non-spherical particles? Because now we have steric effects of a type, as particles have to sweep out a certain volume to move or to rotate into a preferred direction, that becomes another degree of freedom in manifesting their jamming potential. And irreversibility. If you reverse one of these highly ordered ones, it goes from an ordered to disordered state and can actually jam again. So here's our last couple slides, how we're going to do it. This is a melt-present blob of living mush from the Galapagos that was brought up by a volcano. These are crystals right here. This is good green. There's a calcium color map. So this is an example where maybe we can work with something like this. But DEM is a brute force approach. It's really a brute. It's very powerful, but it's a brute force approach. So maybe the next step forward, and I had a great conversation with Karen before she left, was asking, can we represent this as a network? In other words, replace the natural system with a mathematical object, a representation, that then we can do all kinds of interesting things to hunt for clusters, do the kind of stuff that Jeff was talking about, and advance our understanding rather than just hitting it with DEM through this approach. So this is my mush going forward, and that's it. Thank you very much.
And then Olivier next. Great talk. Thanks, George. So I just wanted to make sure you do have a fluid in your simulations,
Yes.
right? And since you have a relatively coarse spacing, how do you take the fluid force onto the particles into account? Is it mostly just a drag force?
Yeah, it's basically a drag force, and there's a whole kind of zoo of drag forces you use because the projections aren't simple, depending on the direction of flow and the area and shape projected. But these things are so dense packed and they're moving so slowly. It's really it isn't a large part of the problem, it seems.
Does the fluid exert a torque at all on the particles or not?
I don't know. I'm thinking our motion is probably so simple. The fluid's being driven by the flow itself. So it isn't, there's no external, the fluid doesn't have any movement except that which is being driven by the plate. And once it undergoes Reynolds dilation and reaches its steady thickness, there isn't any more pore pressure effects. But that's a good question.
All right, thanks.
So the crystallization dynamics itself is separate because of the temperatures?
Yeah, we didn't, that's a great question. We're assuming that the crystal growth time is long compared to the mechanical problem. And also, we just needed to sort this out before we started adding effects of reactions and, and anything like that.
Okay.
George, as shown on your last picture, mini-crystal in magmas are angular.
Yeah.
So can this be critical regarding the simulations where the elongated particles are not angular?
Yeah, that's a great question. Using a super ellipsoid kind of representation for the particles limits that piece of it. But we did the same simulations with the LMGC90 code, from the Montpellier group, which does have sharp edges. But because it's not distributed parallel, you can't do that many particles. But we found the same kind of behavior when we used their code.
Okay.
Yes, thanks, George. That was very fascinating. But I had a question about your, you have this shear flow in the DEM with a porous boundary condition. I was trying to understand the relevance of that porous boundary condition relative to what happens in nature in terms of being able to exchange basically the molten rock with that, right?
Yeah, well, I guess then we have to ask the question, what's the characteristic pore pressure equilibration time scale? So, because otherwise, as we were talking yesterday, you get this kind of pseudo lubrication effect where you can't pull particles apart because you can't pull fluid in. And so, but we felt we had to include that. I'm trying to think again how to answer your question. You know, our viscosity here is 10 Pascal seconds. But that's why this is basically taking place in an immersed environment. Mm-hmm. So the fluid can move in and out in response to the Reynolds dilation.
But you could, in principle, make the permeability to get in and out of the system something that would set the time scale for that, because that would force the pore pressure to go up to be able to suck material.
Yeah. Well, you know, and this is one thing we were asking ourselves. I'd like to calculate the permeability from these experiments, but trying to do some sort of voxel rendering or tessellation on those is really time consuming. It's especially in 3D. You have to hunt for where the boundaries of the particles are and then calculate the void and then the tensor of that permeability. But I'd love to do that.
George, in the natural systems, though, there are segregations of fluid-rich regions, right?
Thanks for a fascinating talk. I wanted to ask, did you consider incorporating like a growing crystal in time in the midst of the simulation, or at least changing morphology?
No, we didn't. In part because, you know, it took these things take months on my supercomputer, and we're just doing small pieces of time. The time scale for crystal growth is long compared to the time scale that is available to us as a practical thing.
Okay, yeah, thank you.
We'll take two final questions, Kimberly and then Prabhu.
Just to clarify about the simulations, I was also wondering if you do lubrication forces. I didn't hear that.
Well, you know, we didn't in this one. We published a paper on lubrication forces before, and we found that really they were only important in the transients. And once we hit steady state, they didn't seem to be contributing. We did, you know, because lubrication adds a lot of cost to the simulations. But we did basically a set of parallel runs where we had lubrication forces and not. And there were differences in the transients. But there weren't many differences in the steady state behavior, like the critical state behavior. So we left them out of this one because also calculating lubrication on these curved surfaces, you know, for spheres it's pretty straightforward. But when you have this with the irregular pore shapes.
And then I was thinking about Jeff's question about the fluid coming in and out. I don't know like how in this sort of simulation one would sort of look at the pressures, except for maybe through the lubrication forces, like make them more pulley than outwardly. So just, you know, a thought for the future if you do include something like that.
So, Michelle and I were just talking about the orientation effects in shear localization that you seem to observe. So there are two ways of thinking about it, I mean, to me. One is, you know, there's a difference whenever you have particles that are orientable. There's a difference between their rotation and the mean vorticity, right? So that causes localization. The other is even if you don't have orientable particles, you do observe localization, and there are models that are able to determine the localization. Have you tried to think about any of these?
Well, we have, because we saw localization even when we were doing spheres, you know, and basically strain becoming highly localized, and what I call them soft faults are basically fluid present, you know, differences where the entire system, one part's frictional and the other part they're separated along a plane. So we recover that phenomena even with spheres.
Sure.
Yeah.
Sure. Right. Yeah.
So it seems to be a pretty robust observation, but we haven't actually pursued in detail the micromechanics of it, and I appreciate your input, and I'd love to hear more and chat with you more about this.
Let's do that.
It'd be great benefit to us.
So let's thank George once again.